So this morning, we're going to look at the topic permutation and combination. As a matter of fact, a lot of the textbooks, you might see them use a big word to refer to the study of permutation and combination. And there's another word, combinatorics. Right? And it's basically the study of counting principles, permutation, combination. And you'll also have a lot of probability involved as well, right? Because in probability, you often want to know total possible outcomes or, favorable outcomes and so on. For that, you would need to do some counting, right? And depending on what conditions are prescribed, well, you might have to use either permutation or combination. In just a moment, we'll learn what are permutations, what are combinations, right? Good. So we're going to look at all of these, right? We're going to look at we look at the fundamental principle of counting first. Then we'll talk a little about permutation and a few theorems, of course, with some examples. Then we'll briefly look at combination, how it differs and so from permutation. And you will see that there is a kind of confusion in how we use the word combination, right? And then we look at some examples, right? So let's start. First, we look at the fundamental principle. Oh, my bad, that word is spelled wrong. This should have been, this is not, what has happened here? Yeah, this should be principle and not, yeah, right? Fundamental, I hope no more spelling. Sometimes you type these things and, the internet does its own thing. Fundamental principle of counting and not principle, right? Sorry about that. Yeah. So here it's saying that if an event can occur in m different ways, following which another event can occur in n different ways, then the total number of events which occurs is m multiplied by n. And I know when you look at, you hear about event, sometimes you want to know what is that and so, right? But we'll come to that in the next slide. Look at an example. So in this example, it mentions that Rohan has 3 shirts and 2 pants. In how many ways are the combinations possible, or how many ways can he combine these outfits, right? On any particular day, right? So wearing, maybe let's say we have a pink shirt, we got a white shirt, we got a green shirt, we got a blue pants, we got a white pants. So wearing a pink shirt is an event, right? So don't think of an event as some social occasion only, right? No. So and sometimes you hear that term. Sometimes you say, in the event that I wear jeans tomorrow. Have you ever heard somebody say that?
Yes, sir.
Yes. In the event that, tomorrow Sir pop a quiz on us, right? So sometimes you hear the word in that sense, and that's what we're talking about here, right? A possible outcome or a possible, something that can happen, possibly happen, right? So Rohan wearing a pink shirt is an event. Him wearing a blue pants is an event, right? So if he has 3 shirts and 2 pants, well, how can he, how many different outfits then, or you can put together, right? Well, if there are 3 shorts and two pants, the total number of ways you can arrange them is 6 ways, 3 by 2, right? And that's the fundamental counting principle at work there. And you can see that, right? Like you can wear the pink short with the blue pants. You can wear the pink short with the white pants. You can wear the white short with the blue pants, You can wear the white short with the white pants. And then you can wear the green short with the blue pants. And you can wear the green short with the white pants. So you see how many outfits? Just when he think he's poor and he doesn't have too many clothes, he could go 6 days to UG, right? Wearing different clothes then. He doesn't have like an outfit that is identical to the other day. Right? So if you have just 3 shorts and 2 pants, you can come looking different at UG every day. Because I know a lot of you don't want to wear the same thing 2 days. Like me. When I used to go UG there, I think I had 2 pants maybe. And people want to know. As a matter of fact, I build my wardrobe around same colors. You think I always wear the same clothes, But I just have a lot of identical pants or they're close in color. You don't really know, right? Some people do that. But if my clothes were very different in color like these, I can still come looking different. Good. So that's a simple application there of the counting principle. So what's a permutation? I think you heard the word combination before. I want to think that, I know that a lot of people, they use the word combination to even mean what we refer to as a permutation without knowing, and you'll see. So this is what they're saying a permutation is, right? It says a permutation is a way, especially one of several possible variations, right? In which a set of numbers of things, a number of things can be ordered or arranged, right? That's basically the bookish definition. In the area of mathematics, though, right? I guess when you Google permutation, they'll give you that bookish definition you see at the beginning here, right? That's this definition here, right? That's this here. I'm not sure Google will give you that, but I think that's where that came from. But this is the definition that we are going to pay attention to, right? So it's saying a permutation is an arrangement, right? So we're talking about arrangements here in a definite order of a number of objects taken some or all at a time, right? So maybe you have a set of objects, right? And you want to know, well, how many ways can I take? Let's say you have some red marbles, you have some green marbles, you have some blue marbles. And you want to know, well, how many ways I can take, 3 marbles from all these marbles. And, one is going to be red, one is going to be blue, one is going to be green. That's an example of, you have a set of different objects and you're taking 3 of them, right? Well, how many ways you can do that, right? Of course, there are other times when you want to select all of them, but order and so is important and so, right? Notice what they mention here. Whenever we deal with permutations, order is important, right? This is very, very, this is something here. So in permutation, order is important, right? And keep this in mind because you will see that very often when you use the word combination, what you really mean is permutation, right? And you'll see examples in a moment. So this is a little formula, right? For permutations, and this is what they're saying. The number of permutations of n different objects taking R at a time is NPR. That's how you write it. Different books would have it differently. You can see some books will have this. They have this. Yeah. They'll have N and the P is going to be there and the R. No problem. No problem. Right? I think your calculator. I don't know how it's on the calculator. Sometimes it's like that, right? Like just like this here. Yeah, just like this. Right? And the formula, the formula to explain what this is calculating is this here. Right? NPR is equal to, now this is new. This here is new. What is that? N factorial. What does that mean? Let me use some examples. Let's say I have 5 factorial. What that means is this. 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1, and whatever that is equal to, that's 5 factorial, right? Some things 0 factorial, 1 factorial. Just identify on your calculator there factorial for me. Everybody with a calculator or a cell phone, do the 5 factorial thing for us first.
Is 120, sir.
120. Okay, 120 here. 120. Check 0 factorial.
1. Yes, sir. 0 factorial is equal to 1.
Check 1 factorial.
And 1 factorial is equal to 1.
Yeah, right. So this is a peculiarity to factorials, right? And later on, if you study mathematics a little more, you're going to get down to the proof of all of that and so on. What we're concerned is you just understanding this factorial notation and how to use it. And mind you, you don't even have to use this formula because this formula is built into the calculator, right? It's built into the calculator, right? And you can see here that if you're choosing, let's say you have 5 objects, right? To choose 5 from it. What would that be equal to? Right? How many ways you can choose 5 objects from 5? Well, 5 factorial over 5 minus 5, which is 0, right? So you get 120. Right? And this is if, as I mentioned, that the objects are distinct, that's one, and order, we go back to the previous, let me see. We go back to the previous slide. It says when order is important, right? So let me just let me go back to this one here, right? And if we're talking about 5 objects, let's say you get a 5 objects, or let me go down with a smaller number, right? Maybe 3 objects. So we get something like that, something like this, and a star. 3 objects, right? So we realize that these 3 things can be ordered in 3 factorial, right? Ways, which is from the formula, right? And the denominator is going to be 0, which is what? 6. 3 by 2 by 1, yes, 6 ways, right? Now, if I put, okay, I put that, that's 1 way. Then I put maybe this. What's happening? Sensitivity is a problem. Yeah. Oh, it's the same combination of things because it's the same three things, right? But the order is different. You see, order is important. Then I can probably put star 0x. Then I can probably put what I can't figure out all six of this thing. Help me. What can I put for us here?
You can get x star
X
0.
star
Star
0.
0.
We have to get how much more? Two more?
Um,
Give me another one.
You can get
0 star X.
Yeah,
Zero.
0 star X.
Star X. You gotta get one more, or else the counting principle in trouble. I'm getting 1, 2, 3, 4, 5. What's another one?
Star x 0.
Star
Star X
X.
0, right?
X 0.
0. See? So instead of, well, what is this? Yeah. Yeah. Instead of having to write out all these possibilities, and my eyes are dazzling me, I can't follow, the different arrangements, right? But if you want to just know the number of different arrangements that you can have, well, we use that formula to actually get, what are the specific arrangements. Well, you have to do this, right? Yeah. But this formula can give you this very easily. But notice, when in every one of these arrangements, it's the same 0, x, and star we use. Not so? It's the same thing. So it's the same combination, but a different arrangement or a different permutation, right? And later on, when we get into combination, you see that difference in the definition, right? So in permutation, the arrangement is important because look here, this arrangement is different from this arrangement, but they're the same tree, thing. They're the same tree thing, right? So that is important. How you arrange it is important in permutation. Keep that in mind. Right? And of course, keep this formula in mind. You don't have to fight up with this formula because it's built into almost any and every calculator that is out there. I think even your cell phone. Is it on your cell phone calculator?
Yes, sir.
I think so. I want to think so. I hardly think there's a calculator without it these days. Right? Otherwise, the drawing isn't clearing. All right, we cleared this here. It's like it's permanently on. Did I save this onto the I probably saved this onto the slide. All right, I'll fix that later. Yeah. Yeah. Okay. So this is another example. So you're asked how many different signals can be made by 3 flags from 4 flags of different colors. So, this kind of thing used to be done long ago, when maybe men are in battle and they're far. They might have different color flags. I don't know if you ever see that in the movies or in the history books. So you got 4 different flags, and you want to send a message to your other, the group of men or the other battalion of soldiers some distance away, and there are no radios those times, right? So what do? Well, you come together, of course, make arrangement that, okay, when you see this flag, and this flag wave, you must understand that we mean this, So how many different, well, I'm sure your mouth, just like mine, wants to use the word combination. As a matter of fact, they used it here, right? They used it here. Notice this. Notice they use the word combination, right? And oh, by the way, these slides are this slide is not mine, right? So I borrowed it off the internet. Yeah. So because we haven't really defined what the combination is, we're going to use the word very loosely. And it is because you are familiar with the word combination. Well, we're going to use it, right? You are thinking of combination in your mind, when in reality we are doing a permutation. So how many different ways you can arrange 3 flags if you have 4 in all? How many different ways you can, you can make a signal with 3 flags? Well, simple, 4p3, right? And the answer is 24. The calculator will give you that. But I want you to understand what that means, right? You want to take, you have 4 flags. You want to say, all right, maybe one time you take a red. I don't know if you call this mauve, or do you say this is purple? What would you call this second one?
It's purple,
I would
sir.
say this
It's
is
purple.
red. Purple. All right, let me go with purple. This is what, black or green? And this is blue. I'm colorblind, right? So yeah. So maybe one time you do red, you do it in this order. Then the next time maybe you take red, the black, and then the purple, right? Maybe then you take the purple, purple, black, and then red, and so on and so on and so on. Then you have those that would include the blue at the end here, right? And if you were to take your time, let's say you want to prove me wrong, we'll start talking 24 different ways I can arrange these things. You know, if I take 3 at a time, you can write it out in your own sweet time. And I don't know if there's a piece of software online that can actually do something like this for you. You know, you can check to see whether and write out all the combination. Well, I'm calling it combination, but really and truly what we mean, right, is permutation. Because let me just show you something. If you get red, purple, and black, and then let's say the next time you get purple, red, and black, it's the same combination, right? It's the same combination. What's different is the arrangement, and that is why later on you realize that this word we have been using and is in our vocabulary, even this author used it. He's using it because he knows you don't know the difference between combination and permutation yet. So what they're referring here, right, is really how many permutations you can get, not necessarily combinations, right? Keep that in mind. Are you understanding what I'm talking about? Give me some feedback.
Yes, sir.
Yes, sir. Yes, sir. Tracking. Yes, I understand.
Yes, sir.
And here is an analytical approach to how they came up with that 24 ways. So you have to make a signal with 3 flags. So the first flag that you're going to use, you got 4 flags to fill that space, right? So you say, all right, good. How, oh, by the way, in this problem, the assumption, right? The assumption is that you are not repeating. You are not repeating any flag, right? Like notice in none of, none of the combinations, right? Or I'm saying combination myself, or the permutations, you don't have like red, 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 you know, or 3, no, did I say 4 red, 3 red, 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 no, right? Because that can be confusing too, because the man would say, wait, he said red, but what happened? Wave back red again? No, so you use a different flag for every wave, right? So you wave a red one, then you wave a purple one, wave a gray one, you know? Yeah, so there's no repetition here, right? So the first flag, you have 4 flags to choose from, right? You have 4 flags, and that's why I say you can fill that first gap or that first wave of the flag. You have 4 ways or 4 flags to choose from. Then once you have chosen one, right? Well, and the assumption here, well, the way the drawing is, right? It's as though you chose the blue at the end as the first one. For the second flag that you're going to wave now, you can't wave back the blue one because that will confuse your people and who you want signal, right? you have 3 only to choose from, right? And let's just say you chose the black or gray or whatever you call that third one. Now in the third wave now, you only have 2 to choose from, you see? And if you were to multiply 4, remember the counting principle now, counting principle. If you have 4 possible events, then you got 3 possible events and you got 2 possible events. The total number of possibilities is 4 by 3 by 2, right? And that's how they get at 24. But if this analysis is too hard and long for you, well, we have that simple formula, NPR, which is 4P3, right? You just use that. You follow this?
Yes, sir.
Yes, sir.
Yeah, right. So most of the time you wouldn't be using this approach. You would use the formula, but of course, if you want to analyze it like this, and if you want to go further, if you want to go and maybe have a software or you want to do it by hand, write out all the possibilities. Well, good luck with that, right? Because if I say that maybe get 10 flag, you know what will happen there, right? Okay, good. So here what they say here now. There's another theorem that has to do with permutation. So the number of permutations of n different objects taken r at a time, and here this part, repetition is allowed. How many ways now you can arrange these things? Well, notice what I said. It's n to the r power. So here, repetition is allowed because just now what? You got a 4 flag thing, right? So if okay, let me show you. If you have you have 4 flags. So then it means then that you can arrange, all right. Let's say you're dealing with red, right? And you have to choose 3, right? So you get what? Then you have red, red, red. You understand? And then you can have yeah. You have, what was the second one? Purple, 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 purple. You can do that, right? So these never they weren't in the original problem because repetition was allowed. So you know how far more you got. What was it? Blue, 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 yeah, black. Oh my, blue and black would be same thing. Black, black, black. You know, so that would cause more possibilities now, right? More arrangements. You see, if you can repeat flags. So apart from, combining the different colors, if you can use the same color more than once, you have more, right? And for that reason, the number, of course, if you realize n to the r is greater, right? So 4 to the third power is a bigger number, right? 4 by 4 by 4, whatever that is, right? What's that? 4, 4, 16, 4 is how much, right?
64, sir. 64.
64. You see, far more possibilities if repetition is allowed, right? But I would think just for gaff's sake, right? When they were doing those signals, I don't think they might repeat colors, Especially I wouldn't think they'd repeat it one after the other. They might have a red, they do another color, then maybe come back with a red, right? Just to increase the number of possibilities. But repeating it, one after the other, red, 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 3 times. Well, maybe it can be done, yes. It can be done. Let me not make a rule. Good. Good. So look, we have another example. So you got this word nuts, right? And I'm not referring to any one of you, right? Don't feel guilty. Don't feel sorry throwing this example. And don't go tell people I call y'all nuts and so, right? So you have this word nuts. And you want to make words, 3-letter words from this 4-letter word, right? So you want to make up the 3-letter word. So notice You either can use that formula, what was it? 4 to the third power, or you can use this analytic approach that they're putting, right? They're proposing here. So the first letter can be any of the 4. Oh, notice it says repetition is allowed, right? So in the first letter of this word you want to make, you get any of the 4 letters to use, N-U-T-S, right? That's what you're seeing here. Yeah. You got any of these here, you can say, all right, let it be N. Second one, you got all the letters again. You can say N, right? And here again in the third one, you get all the letters to use again. I could say N again, N and N. I don't mean that our word makes sense, right? But I could do that. But there's nothing to say I have to use N-U-T, then S-U-N. No, I can use back N how many times I want, right? I could use back U anytime. So I have far more arrangements, right? Of letters. So the answer will be, well, 4 by 4 by 4. But let me ask you a question. Let me put you to work a little. If you can make 3-letter words from this without repetition, how many will we have? And what formula will you use? You're making 3-letter words. Oh, and those 3-letter words need not make sense, right? You don't care whether they're real words in English. Hmm? Anybody? So repetition, in this case, repetition is allowed. We got the answer there. But let's say repetition is not allowed.
So you use the MPR formula and get 24.
Yeah, very good. So it's 4P3, and I think, oh, that works out to be 24. Yeah. So this the NPR formula is when repetition is not allowed, right? Arrangement is important, but repetition is not allowed. Keep those things in mind. I know it's new. You know, some of you are afraid to answer. You might be wrong, and so because this is something new, right? And it's good that you're learning this. As a matter of fact, it's good if you had learned something like this as early as high school, because your brain will be young then, you know, and you'll be able to kind of wrap your head around it and play around with it in your brain, because you know your young minds can handle this thing better than my older mind, you know. Good. So let's go to another one. Well, they have it here, right? This is using the formula. They showed you, you know, analytically how you would have gotten the 64. Here they're using the formula, right? Good. So here's another theorem, and this one is taking it a little too far, you know, for your level, because you're now being introduced to permutation. But nevertheless, you have sharp minds. You will be able to handle this. Here what it says. So you want to now you want to arrange things, but maybe they're identical objects in the set, you know, in the whole set of objects that you're arranging, you have identical ones. You know, sometimes you got some, let me say, we dealing with words. You all had some words just now, like nuts and so. But you got some word where the letter repeats itself, right? You know that. Sometimes you got 2 E's or 2 A's or 2 I's in a letter. I mean a word. And well, to arrange those, well, what do we do then, you know? And sometimes you know, okay, let's say you know marbles, you know, get two marbles of the same color. You're arranging books on a shelf. You probably can have, I know when you are going UG library there, right? They got some identical books, right? They might have 4 copies of, let's say a book we use, calculus with analytic geometry. They have about, I think about 10 copies in here. You know, so you have identical objects within this whole set. how do you treat with those? Well, this is a little thing here. Here it says, the number of permutations or arrangements of n objects where P subscript 1 objects are of one kind, P subscript 2 objects are of a second kind, and so on, up to PK objects are of the kth kind, right? Is, and often you don't get like, you might not have P1, P2, P3, P4. No, you might just have like one or two objects, they have a couple identical ones, right? Yeah, so the formula is n factorial over P1 factorial, P2 factorial, right up to, if you have, right, so many. Sometimes you just have two objects that, well, there might be several of them, right? You don't have to go on to PK, like 4, 5, 6, you know, no, you don't have to go on. But there just is a general formula, right? It's a general formula. An example would really illustrate this, right? So let's go to an example. So what's this? So they're saying find, okay. I think they mean find the number, they're talking word the. Find the number of permutations of the word Allahabad, right? I borrowed these slides from a guy from the Middle East. So this is a place over there, no? Allahabad. I think so, right? This says nothing about anybody's religious persuasion, right? I just borrowed it from somebody there. So Allahabad, and you would notice like they got two L's, they have a couple well A's. Anything else is identical? I'll help me with your young eyes.
No, sorry, just the A and the L.
Oh, okay. They have 4 A's and 2 L's, right? And everything else is kind of different, right? Or distinct. So you have 9 letters in all, no problems there. A repeats itself 4 times and L repeats itself 2 times. And all the other letters are distinct, right? Or they're different. So you want to know how many ways you can arrange this word Allahabad, right? So simple. You apply the formula. 9 factorial over, you got 4 A's, 2 L's. So 9 factorial over 4 factorial, 2 factorial. And well, the calculator will do that for us, right? 7,560. Right? And the only way, I mean, there are proofs, right? There are proofs for these formulas. But I think at this level, it may be a little beyond you. You want to do a little more mathematics before you can be able to handle the proof. You can verify these things with small numbers. Like you won't go with a number of 9, a word with 9 letters to try to verify this. You probably want to start with small numbers and see that it works, right? And because you can actually list out all the possibilities, right? Or you can have, I don't know, there's some software or some website that would simulate this whole thing and give you all the possibilities, right? There may be. But what I'm saying is that you can do it by hand with small numbers. And I guess the mathematicians actually look at patterns as they increase the number. So maybe they take let's say a word with 3 letters, 4 letters, 5 letters, and then they, you know, maybe have 2 identical letters, then another, you know, another letter that is identical, and they build from there, and then they came up with general formulas like this one, the n factorial over P1, P2 factorial, and so on, right? But for now, we'll have to just take it at face value. Another example. So you got, in how many ways can 4 red, 3 yellow, and 2 green discs be arranged in a row if the discs of the same color are indistinguishable? I don't know if you understand what that means. The 4 red, you can't tell which one is which one. Well, you know that, right? If you got like 4 red marbles, you can't know which one is which one. Unless you put a mark on them, like this one is 1, that one is 2, that one is 3, that one is 4. No. But if 4 red is 4 red marbles, you don't know which one is which one, right? Same thing with the 3 yellow, 2 green. So you want to know how many ways you can arrange it. Well, same formula again. You got how many in all? 4, 3, 7, 2, 9? 9 marbles in all. So your numerator is 9 factorial. There are 4 red, 3 yellow, 2 green, your denominator. 4 factorial, 3 factorial, 2 factorial. And that's your answer, 1,206. Right? I know I'm giving you this formula and saying, where did this thing come from? Good. So this one is a little more involved, right? This one is rather long. Can I ask you to snip this and have it somewhere or write it? Because the solution of this one, I usually just avoid going through this solution because it takes up a number of slides. It takes up a number of slides, and therefore, sometimes you lose track of what are we doing really. Have you taken a copy of it, maybe? Maybe you snip it and keep it? Or write it or something? Do that. So when I, when I go through it, you'll be able to refer back to, okay, when we're doing part 1, maybe when we reach part 3 and 4, you say, well, what are we talking about, you know? So you want to find the number of arrangements of the letters of the word independence. In how many of these arrangements, well, they want, do the words start with P, right? And then do all the vowels, well, how many of the arrangements do all the vowels always occur together? So all the vowels, yes, which vowels? It's only I and E, right? I is a vowel, yeah. I and E. And then it says, in how many of your arrangements do the words begin with I and end in P? And then the last one, repeat part 4 with I and P interchangeable, right? What's all of that? Well, we gotta break it down piece by piece. So let's see, we got this word independence. And we're trying to make all the possible words we can get within these letters, right? Good. Okay, all right, before we go to the thing, how many possible words can we get with the word independence? How many letters are there? Before we go to it, well, at least you should be able to answer that easy question. So you got how many letters?
Yeah, 12.
12, okay. So how many arrangements can we have with that? How many arrangements can we have? That shouldn't be hard. I don't mean give me the number. Tell me how you want to calculate it. And you can calculate it, of course, with a calculator. 12 what?
Factorial.
12 factorial, right? So punch it in the calculator. Let's see. Oh, so it's a big number. No, they didn't say, okay. Well, 12 factorial, that's the numerator here, right? That's the numerator here. Good. So remember the first part. Oh, we have some identicals inside, right? We had how many? 4 of what we had? I already lost the word. Independence. Four what? That's E?
Yes, sir. 4E.
3 what? 3 Ds? No. N appeared 3 times and D appeared 2 times. Oh, so because of those identical letters, you have to divide by 4 factorial, 3 factorial, 2 factorial, right? So yeah, if the 12 letters were unique, right? They're all different. Well, then the number of arrangements would have been 12 factorial. But because, yeah, I even get caught with that. Yeah, because we had some identical letters, you had to do some division here. So your total number of possibilities, you know, would be what? What is that number? 1,663,200. I hope that's it. Yeah. So what I say is, okay, we want to find out, well, how many arrangements. P is going to be the first letter. P is going to be the first letter, right? So I say let us fix P at the extreme left position. So now, if we are going to put P at the beginning, we get 11 letters now to play around with, right? And that's what you're seeing. So with 11 letters, well, the number of possibilities is 11 factorial. But they got some identical ones, which I seem to forget just now, right? So they still got the 4 E's, not 4 E's, yeah, 4 E's,
Yes, sir. 4E.
3 N's, and 2 D's, right? So in that case now, you only have, what's that? 138,600 ways you can arrange the letters.
Yes, sir.
Right? Yes, so that's the amount. Because the first position is already taken with P, right? You only got 11 to play around with now. You think you get that one so far? Because this problem is going to be very involved. By the end of it, we'll all be lost almost. So is this part clear?
Yes, sir. This is.
Yeah.
So you got this word independence. P got to go in the 4th slot. You got 11 slot to fill, right? So your numerator in that formula will be 11 factorial, but you got some identicals, and that's what you put in the denominator. And you get that, right? Good. So next they ask you, what was the question? They ask you next that the vowels must be
The
be
vowels
together,
always occurs together.
yes. So the vowels must always occur together, right? So here what I said, there are 5 vowels in a given word, 4 E's and 1 I. Okay. Since they have to occur together, we treat them as a single object, right? And they give you the I for the time being. This single object, together with 7 remaining objects, will account for 8 objects. You all see that? So they take all as though all these vowels got to be together. I know you can, in your mind, you say, but the vowels can be arranged like I can go in the 2nd space, I can go in the 3rd one. So we could come to that just now. For now, treat all the vowels as one. You know? It's like, you get a set of books on a shelf to read, but all the calculus book must be together. It's like you paste them together. Right? You put them together for now. Good. So you have 8 to arrange. And then again, among the 8, you got 3 what? 3 N's and 2 D's that are identical. So those can be arranged in 8 factorial over, let me go back here. Yeah, that's this here. 8 factorial over 3 factorial by 2 factorial, right? So you rest that down, right? Now, don't forget that these, the 4 E's and the I, they can be rearranged. They're together as vowels, but they can be rearranged because I can come first, I can come second, I can come third, I can come fourth, right? So you want to know, well, how many ways you can arrange these, how many of them? 5 of them, 4 E's and I, where 4 of them are identical. Remember the 4 E's? So it's this formula. It's the same formula modified now because you have 5 of them, but 4 are identical. And you get a number for that, right? Whatever it is. So the total number of ways you can arrange the word such that the vowels are together is this number multiplied by this number, which gives you this number. So it's getting harder. It's going to get much harder after this. I wouldn't ask you something this involved, you know. But these are good exercises in bending your young mind, you know. This is a nice question for something like an assignment where, you know, you're able to play around with the numbers and the formulas and make sense of the problem and so on. So let's go to, what was it, part 3 now? Could anybody remember what was the part 3 about?
The vowels don't occur.
What is it?
The vowels don't occur.
Oh, they don't necessarily have to be together.
Never occur together.
Oh, never. Well, okay. Well, a smart thing now. The total way you could arrange was this. And when they occur together was that. So you subtracted 2, right? So this was when anything goes. This was when the vowels are together. So these here will be when the vowels are not together. Right? So that was pretty simple. Did I say getting harder? No, man. I think like it get more easy. Oh, sheesh. So what was the 4th one?
I in front
Like-
and P at the back.
Oh, yeah. Oh, okay, good. So you see, this is similar to the earlier parts, like part 1,
With the P.
1 or 2. I can't remember part 2 where P had to go in front, right?
Part 1, sir.
Yes. Yeah, there was one where P had to go in front. Well, this is just something similar. I got to go in front, P at the end. So those 2 are taken. You got 10 left, right? So 10 factorial over the identicals, right? 4 E's, 3. I don't know what 3 was. Which letter was 3? N?
N.
3 N? Independence, yes.
Yes.
And 2
D.
2 D's. Okay, yes, right? So you get, you make sense of all the numbers here. There are 10 letters left, and then there are some identicals inside, and that gives you that number. The problem is finished there. I think there's a 5th part now.
Yeah, one more sir. When you're interchanging P and I.
And the same repeat same parts as part 4, as I and P are interchanged. Right? So I think this word spelled wrong here, right? Excuse the guy. The guy is from the Middle East, right? So he would make some, I mean, you and I from right here and still making these mistakes. Yeah. I hope the word interchangeable to is spelled right. Yeah. Yeah. So let's say as I and P are interchangeable, they can further be arranged in 2 ways, right? So can anybody read that fifth question? Let me just make sense of it.
repeat part 4 with I and P.
And part 4,
interchangeable.
I have to be in front and P at the end, right?
Right.
Huh?
Yeah. I in
Yes.
front of it.
Good. So they're saying that I and P can be interchangeable. So it means that I can be in front and P can be at the back. Right? You see when you had I in front, when you had I in front and P at the back, that kind of restrict your number of arrangements. But if you can put P in front and I at the back, that will give you, you know, a lot more, or as a matter of fact, they tell you twice more the number of ways you can arrange the letters, right? And that's what they did there. Right? So you take the previous answer and multiply by 2, right? And you'll get your answer. Well, let's say 2 factorial. 2 factorial is 2. And this is a really, really involved type of problem. It's a type of thing you do on an assignment, you know, take a couple of well days and make sense of it. Right? So let's touch quickly on combination. This is the last thing. So let's take the mathematical definition that we are concerned with. That is easier. Right here. Right? And please note this. So a combination is a selection of some or all of a number of different objects. Notice it is an unordered collection of unique sizes, right? In other words, what they're telling you, order is not important. Order is not important. So if you have, let me say, go with, if you go with, we had this example earlier, 0, X, and a star, so right? This, if I put here this, and this, these two are an identical combination, right? It's an identical combination. It's just like, okay, if you got a plate of rice, but one man chicken there here, right? Or no, let me say this is a little bread, a piece of salt, you know, you call it bread like. Down here get a salad, and a man get a nice chicken here, right? But the next person plate, the bread there down here, right? And mind you, I could take the same thing and just spin it around. Let me just say, the next man get a square plate. But he got the chicken here, he got the salad here, and he got the wrong bread there. Same combination. What you two fighting for? What you all fighting? Same thing. You man got the same bread, same chicken, same salad. Right? Right? Because it's just oriented differently. Right? So keep that in mind as the difference between a permutation and a combination. Right? And let me bring that out. Let me see this other slide got it. No. Let me go back. Yeah. You know when you all talk about combination locks? You know combination locks, like, okay.
Yes, sir.
You got a lock and all right. 1, 2, 3, or even your password. Let me take your password. Right? Let's say you get a combination lock. Now, let's say your combination is 1, 2, 3. Does 3 to 1 open the lock? Does 3 to 1 open the lock? If your combination is this, 1, 2, 3. Does 3 to 1 open the lock?
No, sir.
Huh? Yes or no?
No, sir, you cannot open.
No. Therefore, that lock is not a combination lock because 3 to 1 is the same as 1, 2, 3. We're using the word wrong all the time. It's a permutation lock. But if you tell anybody that, they chase you out the store, madman searching for permutation lock. You gotta go make the buy. But it's really a permutation lock because 1 to 3 is different from 3 to 1. That's a permutation, right? Each is a permutation. So keep that in mind, right? In combination, order is not important. Like, oh, You know what's a good example of combination? Lotto. How much number you gotta choose for Lotto now? 26?
28.
28 number now? Oh my, they're making it harder, man. Yeah. So if you are, let me go with R. Let me just say Lotto needed 5 numbers. So you choose 2, 3, 4, 5, 7, you know? And 3, 7, 5, 4, 2. So let's say you chose these numbers up here. You buy the ticket and you tell them, give me 2, 3, 4, 5, 7. And tonight when they draw 3, 7, 5, 4, 2. Do you win the Lotto?
Yes, sir.
Huh?
Yeah, you win it. Combination.
You win it, yes, you win it because what? Lotto involves a combination, yes. Right? So the order does not matter. You don't have to get it in a particular order because it could be harder to win too. Why do you think they're jacking up the number of numbers? It's to make it harder for you to collect your money. So yes, Lotto is an example of combination, but the combination lot is not an example of combination. I don't know if that makes any sense.
Sir, question.
Yes,
Sir,
sir.
I'm thinking if when you're finding subsets of a set, if that's the same concept as combinations.
Okay, let me take one. Let me take one and see what you're talking about. So you have a set of, we just get it. Let me say the and star. So this is a set. So you're talking about, all right, subsets. So are these two different subsets?
No.
No, sir.
No, right? So then what are we talking about? Combination or permutation?
Combination.
Yeah, very good. Yes, right? So when you're dealing with subsets, yes, you're dealing with combinations, not permutation. The arrangement, the order is not important. Keep that in mind. Order not important, order not important. Yeah. Good question, Drake. I wonder why when I'm trying to clear this thing, it's not clearing. That's strange. Yeah. Now this is the formula for combination. So, oh, they didn't give the formula? All right, I missed it. They didn't give a formula? What kind of thing is this? All right, the formula is NCR, right? Which is N factorial over N minus R factorial R factorial, right? I hope I get that right. Huh?
I think it's down the next slide. Let me just skip.
Oh, then the next slide. Oh,
let me just skip until we have something like this.
Okay, yes. I find it strange they're going to. Oh, all right. So they're telling you, I think they're illustrating the difference here with permutation and combination, right? So you have 3 teams, A, B, and C. So you can only have 6, you can have 6 permutation, right? Because A and B and B and E will be the same, right? B and C and C and B will be the same, and so on, right? So there are actually 3 teams. So we're not using this here, we're not using this, right? Because that's gonna mess us up. That's gonna mess us up, right? Like if you say team A play team B, that's the same as team B playing team A, right? So if you have 3 teams and you want to match them up, how many matches will you have? Well, you can only have 3 matches, right? Yes, this is the formula, right? You would use. This is the formula. And this is a simple example to close us off. A committee of 3 persons is to be constituted of a group of 2 men and 3 women. So 5 people in all. 2 men, 3 women. You want 3 persons from it. And they didn't say, how many men and how many women. You just want 3. Randomly, you want 3 people. Right? So, yeah, you want 5C3. You want to choose 3 from 5. Order doesn't matter. Right? They have some complicated ones like, okay, let me just throw in one here, just in, so let's say you want 3 persons. Let me go with 4 persons. 4 persons. And let's see, let me go with 5 men, 5 women, right? And the 4 persons, you want 2 men on the committee and 2 women, right? Good. So the total number of, how many in all is that? 5 men, got 10 factorial got it going in the numerator, right? 10 factorial. 10 factorial got it. Good. However, it's not that simple because you have to choose 2 men out of 5, right? So how many ways can you choose 2 men from 5 men? So you get 5C2. And how many ways can you get 2 women from 5 women? Also 5C2. You see? So the total number of ways now, it gets a little more complicated now. That you can get this committee will be 5C2 times 5C2. Right? So it gets more complicated in those cases. Maybe you'll see some more examples in the other what do you call it? The notes that I sent you, right? And well, this is like a summary of whether you are going to determine to use combination or permutation. In one case, permutation, order is important. Combination, order is not important. Just keep that in mind.